Alright, now we've talked a lot about Kc, we dealt with Kc values. There's one other way in which we can measure equilibrium, that is through what we call Kp, where the P stands for pressure of gases. So this has to be an all-gas mixture at equilibrium. But it's very, very simple. It's exactly the same thing as the concentrations, except we use P symbols for pressure as opposed to the bracket symbol for concentration. So if we take a look at this example right here, is what is the Kp, I should say Kp expression for the reaction H2 gas with Br2 gas gives 2 HBr gas. You notice that everything's gaseous, the temperature obviously is high enough to make the bromine, which is normally liquid, room temperature, go up to the gas. So this is done exactly the same way, only instead of bracket HBr2, we have pressure sub HBr2 divided by, and then the two reactants, H2 gas and Br2 gas, written as partial pressures. And that's all. And if we're given the partial pressures for each, we plug them in and solve for the value of Kp. What is not so easy, at least in the way that we derive it, is the relationship between Kp and Kc. And what I mean by that is that if you have an all-gas reaction, you can use Kc, like I said, in forms of concentration in moles per liter, or you can use pressure, or you can go back and forth between the two. They're not the same value, but they're calculated the same way using different measurements of the perspective that we're using. Like I said, moles per liter for aqueous solution and atmospheres for gases. So we're going to derive that equation using Pubnert. Now at this point you don't have to write this down. Again, I'm that kind of teacher that doesn't like to say, here's a formula, memorize it, or remember it. But if you can see where it comes from, it helps you to understand where this came from. So this is for your amusement only here. We know that Kp described as if we have the equation AA plus BB equals CC plus DD, where little a, little b, little c, little d are coefficients, then the Kp is the pressure of C to the little c power times the pressure of D to the little d power over the pressure of A to the little a power times the pressure of B to the little b power. We've already established Kc. It's the concentration of C to the little c power times the concentration of D to the little d power times the concentration of A to the little a power times the concentration of B to the little d power. Now, Pubnert, we can rewrite in terms of pressure, and since this is all about pressure right here, what I'm going to do is I'm going to relate the two together. Okay? So if PV equals nRT, then P equals N over V equals N over V times RT. Well, N stands for moles, V stands for liter, that's moles per liter, that's molarity. That's what these things all explain right here. So I'm going to replace all of these with M sub capital A, capital B, capital C, capital E to look like this. So I'm going to take MRT, or I should say MXRT, where the X is just whatever substance we have in the equation here. And again, we're just using the theoretical so you can see where the same comes from. So the molarity of C times RT to the little c power is what this whole thing is plugging in right there. So this pressure of C is written this way. And the pressure of D is written this way to the little d power. Pressure of A is written as MRT or MART, the little a power, and the pressure of B, MBRT, the little d power. Yeah, this looks like a mess. So let's clean up it. You see that there's a trend of commonality here in these parentheses. So what I'm going to do is I'm going to separate the RTs on one side and the M's on the other. And it gives me RT to the C, RT to the D, RT to the A, RT to the B as one fraction, and MC to the C, MD to the D over MA to the A, and MB to the B in another fraction. Well, I'm going to now change this. molarity means, again, concentration. What I did up there, I'm going to do down here, because I was just trying to show how pulver was related to that. I'm going to go back and change these molarities back to CDAB concentrations. Okay? And that is equal to Kc. So that is Kc right there that I'm going to replace for that fraction. So that comes over here as Kc. This comes over here as that. Now, this is where we have fun with algebra. Since we have the same base multiplying and dividing, we know that when you multiply same bases with exponents, you add their exponents. We know when you divide same bases with exponents, you subtract their exponents. So what we're going to do here is we're going to take, since these are multiplying together, C plus D, and these are multiplying together, A plus B. But the quantities are subtracting, so that becomes the quantity C plus D minus quantity A plus B is the exponent of RT. So we've simplified this into that. Now, C and D are the coefficients of the products. A and B are the coefficient of the reactants. Products minus reactants, that's the change in coefficients. We use N for the change in coefficient. So this is delta N, which means final minus initial, or in this case, coefficients of the products minus coefficients of the reactants. So we're going to have a couple of problems in your homework assignment that's going to use this equation, and that delta N is identified here as that. So let's take a look. We've already taken a look at a problem dealing with Kp. Now let's deal with Kp and Kc. Okay, so Kp, we're asked number 43, this is page 685. And this is number 43. And we're given this equation, given the Kc value and the temperature in Celsius, and they ask us to find Kp. But we don't need to set up the Kp or Kc expression at all. We just know that the formula is Kc times RT to the delta N power. So Kc is given us as 0.28. R is 0.0821. Don't need the labels because it's all going to disappear with the K values here. Times the temperature. Now the temperature is expressed in Kelvin. So we're going to add 273 to this. This is 1173 Kelvin. Don't put a degree symbol there. You don't want one. So times 1173 inside the not put the K there. Anyway, now comes the delta N. Products, 1 plus 2 is 3. Minus reactants, 1 plus 4 is 5. So this is 3 minus 5, which turns out to be -2. So we plug all that into your calculator, and you get 3.02 times 10 to the -5. And that is your Kp value. Okay? Number 45. We have the same kind of scenario, only now we have the Kp and we want to find the Kc. Well, we go back to the Kp equation, and Kp, which here is 6.55, is equal to Kc times RT. Well, R, again, is 0.0821, and the temperature, well, it's 627 plus 273, which is 900 K. That sounds familiar. And we get 56.3 when we do the math on this. Now, 47, I realized I hadn't put this in my notes. Well, that's what I was checking there, so let me go ahead and put it up here. We'll do the first one here, 47A. This is just an example of, actually I'll do B for this. I think I did B already in the notes. For part B, we're just going to write the KC expression, but remember KC involves gases and aqueous only. So the products here are solid and a gas, so ignore the solid and put just the gas, CO2. And in the reactants we have a solid and a gas, and we ignore the solid again. They don't ask for a value, gas or an answer. I think I did part A in the script. Here's part B. So your assignment, practice problems, page 685, 686, because 48 leads into 686, so don't forget to do the last part of number 48 on page 686. Have fun.